Okay, so I'm just going to review pure tests today, and this covers all this section. So look at the study guide and see the topics on there. So this is basically the gist of what will be on your test. So I'll go through these ones a little quickly just because we've gone through them a million times at this point. So nitration reactions, right? This is electrophilic aromatic substitution. So we're adding or we're substituting a hydrogen on an aromatic compound with an electrophile. In the case of nitration, our electrophile is a nitronium ion, and we need sulfuric acid as catalyst. So we do this by reacting benzene with nitric acid in the presence of sulfuric acid, and we end up with nitrobenzene. So nitric acid itself is not electrophilic, so without sulfuric acid, this won't do anything. So we need to make our electrophile, and we do that with the nitric acid and the sulfuric acid. This is the structure of nitric acid here. We're going to protonate this oxygen. So lone pair of electrons from oxygen. It's going to take a hydrogen, and that's from sulfuric acid, which makes a positive charge on the oxygen because we added a hydrogen. Okay, so this is water. This is a good leaving group. So now this bond can break. These bonding electrons will go to the oxygen, and we'll break that apart into water and then nitronium. So now this nitronium, this nitrogen has a positive charge. So now this is electrophilic, and now I can react with the ring. So the ring is nucleophilic because of these pi electrons. It's electron dense, so it can give electrons away to an electrophile. So the arrow will come from one of the double bonds in the ring to the nitrogen because the nitrogen is holding a positive charge. Okay, so that'll break this double bond, and the nitro group will add to one of the double bonded carbons, and a positive charge will form the other one. So to neutralize that positive charge and reform that double bond, this CH bond will break, and the bonding electrons from that bond will go to reform the double bond here, which will get rid of the positive charge and then reform H+, which was our catalyst from sulfuric acid. And you can also write this using the whole structure of sulfuric acid, but it is a bit easier just to use the H+. All good there? Questions? So halogenation, in this case, our electrophile is a halogen cation, and we need aluminum bromide or chloride for our catalyst. So this in itself is not electrophilic, so if we just add these together, these won't do anything without our catalyst here. So again, we need to make our electrophile before we can add the electrophile to the ring. So this is molecular bromine. So when I react with a catalyst, lone pair of electrons from bromine will go to the aluminum and form this bond here, which forms a negative charge on the aluminum and a positive charge on the bromine. So now this bond, this bromine to bromine bond will break, and I end up with a bromine cation and then this counter anion. So this is my electrophile, and now I can add this to the ring. The same thing, the arrow will come from the double bond to the positive ion of the bromine, which breaks the double bond. Bromine adds to one of the double bonded carbons, and a positive charge forms in the other one. And in this case, the aluminum bromine bond from the counter anion is going to attack the hydrogen on the ring. That CH bond will break, and then these bonding electrons will go to reform the double bond and neutralize the positive charge. So we end up with bromobenzene. This hydrogen combines with this bromine here, and then we reform our catalyst that we used up here. Questions? So sulfonation. In sulfonation, our electrophile is SO3. So we do this with reaction with fuming sulfuric acid, which just means it's sulfuric acid with SO3 mixed in, and we end up with sulfonic acid. So this is already electrophilic because we have 3 oxygens connected here, and these are very electronegative, so this is going to make this sulfur electrophilic. So we don't have to do anything to it to make it electrophilic. So air will come from the double bond in the ring to the sulfur, which is going to break one of these sulfur-oxygen double bonds. So this group adds to one of the double bonded carbons, and then should be a positive charge there. My bad. So that group will add to one of the double bonded carbons, and positive charge will add on the other one. And same thing as for this CH bond is going to break, and these bonding electrons will go to reform the double bond. And at the same time, this hydrogen will go to neutralize this negative charge on this group here. You're good. So, and when I just break this sulfur-oxygen double bond here, we end up with an oxygen anion here. So we need to neutralize that, and that gets neutralized from this hydrogen from the ring. So the bonding electrons go to reform the double bond, and the hydrogen goes to neutralize the oxygen. And we end up with this. Make sense? Okay, so alkylation, our electrophile here is a carbocation, and we use the same catalyst from halogenation. So you'll have to be very careful on these because the rearrangement gets tricky. So pay very close attention when you're doing these ones. So in this case, again, we need to make our electrophile. So we'll react to this with our catalyst. So a lone pair of electrons from this chlorine will attack the aluminum and form a chlorine-aluminum bond here, which forms a negative charge on the aluminum, positive charge on the chlorine, same thing as the halogenation. So from here, I would want to break this bond here so I could get a carbocation. But if I just break this bond here, I would end up with a positive charge on this carbon, which would make a primary carbocation, which we don't want because that can't be formed. So what's going to happen is before I even break this bond, I'm going to rearrange this carbocation so it can actually be formed. So what happens is I have a hydrogen here. So this hydrogen will switch to this carbon, and at the same time, this bond can now break. So I switched this hydrogen here, so this hydrogen is now here, and then I broke this bond. So I end up with a tertiary carbocation and the counter ion from the catalyst. Does that make sense?
Yeah, you can just write it in one step, right?
Mm-hmm. Mm-hmm. Yeah, because this doesn't rearrange, or this bond cannot break until it rearranges. Because if we broke this bond, we would make a primary carbocation, which can't be.
We have to separate it and like rearrange it, and then it breaks.
No, you're good, right? They can write it in one step.
Yeah, it's a
Like
one
that.
step.
Yeah.
That's the key.
Yeah.
One step.
Okay, so now we have a carbocation. This can actually be formed, and it is formed. So now this can react with the ring. So the air will come from the double bond, again, to the carbocation, with the carbon with positive charge. So this group will add to one of the double bonded carbons, and a positive charge will add to the other one. And the same, I didn't write this out, the same thing happens here than with the halogenation, is one of the aluminum chlorine bonds attacks that hydrogen, and the bonding electrons go to reform the double bond. So you end up with your product and HCl, and you reform catalyst. So again, be careful here, because you will have to pay attention to the rearrangement. So you have a few different options that this can take place. So you could have like this. So this, if I add to the catalyst, I would want to break this bond, but I can't because then I'll make a primary carbocation. But I also can't rearrange. So what will happen is I'll add this entire thing to the ring, and then it can break. So that is one of your options, is you're about to form a primary carbocation, but you can't rearrange. So you'll add the entire thing with the catalyst still on it. Or you can have the case we just did where you're about to form a primary carbocation, but you have the option to rearrange before that primary carbocation forms. So that's another option. Or you could have a secondary carbocation formed first, which can actually be formed, and then there's a possibility where it can rearrange to a tertiary carbocation. Does that make sense? So we can rearrange before we break that carbon-chlorine bond, or we can rearrange after if we made a secondary carbocation before. Does that make sense? Following me? All good? Okay. So, acylation. In this case, our electrophile is an acylium ion. And we use the same catalyst for alkylation and halogenation. So again, we have to make our electrophile before we can react it with the ring. So this is a very similar mechanism. Lone pair of electrons from chlorine will attack aluminum, make this bond, which makes the aluminum negatively charged, chlorine positively charged. So for the acylium ion, it doesn't matter. It'll form no matter what. There's no like restrictions there. And it also won't rearrange, ever. Okay? So this can always be formed, and this will never rearrange. So I break this bond here, and I end up with a positive charge on this carbon. This is our acylium ion, and then the counter ion from the catalyst. So this is my electrophile. Now I can add it to the ring. So air will come from the double bond on the ring to the carbon with positive charge. And this group will add to one of the double bonded carbons, and a positive charge will form on the other one. So same thing will happen here, where the one of the aluminum chloride bonds from the counter ion will attack this hydrogen and break this CH bond. The bonding electrons will go to reform the double bond, and then you'll form HCl and reform your catalyst again. So you could stop here if this is what you wanted, but the important thing about acylation is that it gives us a way to make straight chain alkylbenzenes, because with alkylation you always have rearrangement if there is a chance for rearrangement, so you can't ever add just like a nice long straight chain to benzene with alkylation. But with acylation, I can have however many carbons I want on this acyl chloride and end up with however many carbons I want here. And then I can reduce this compound using tin and HCl. So remember that reducing agent. So I can reduce this to a straight chain alkylbenzene. And when I do that, I just replace this double bond with the oxygen with two hydrogens. So remember, reduction is losing oxygen and gaining hydrogen, or either one, or both. Make sense? Okay. So these are the important side chain reactions that you'll need to know. So we have oxidation. In oxidation, we can oxidize any alkyl group on a ring with potassium permanganate. This you'll need to remember. This is your common oxidizing agent. This is your common reducing agent. So we can oxidize any alkyl group on the ring, and it doesn't matter how many carbons are here. It doesn't matter if it's branched. It doesn't matter if there's like 10 million carbons here. It also doesn't matter how many alkyl groups I have in the ring. If I oxidize, it's going to oxidize all of those alkyl groups to a benzoic acid group. Okay? So remember this. And then the important reduction side chain reactions. This is one just went over. So when we make this compound from acylation, we can reduce it to straight chain alkylbenzene. So that just, again, replaces the double bond with oxygen with two hydrogens. So this carbon, this one here, and then these three are 1, 2, 3. So here I have nitrobenzene, and I can reduce nitrobenzene using the tin and hydrochloric acid. So when I reduce, it'll reduce to this, because I can't just like selectively reduce some of the bonds here. I have to reduce all of them. So this gets reduced to NH3+, okay? But I want to neutralize that positive charge, so I want to get rid of one of those hydrogens, and I do that with a basic salt, okay? So then I end up with aniline. So point is, you can reduce a nitro group to aniline, and you'll need to remember that. Any questions there? Okay, so substituent effects. So depending on the groups attached to the ring, they have different effects on the subsequent reactions that we have on the ring. So we can have electron donating groups, which donate electron density to the ring. And these aren't all of the groups, but these are the most important ones for you to remember. So electron donating groups, your alpha groups are electron donating groups. OH group, OR, NH2. These are the electron donating groups you'll want to remember. And then electron withdrawing groups that you'll want to remember are your halo groups, cyanide, nitro group, and carbonyl group. These are the important ones for you to remember. So electron donating groups speed up a reaction in reference to just a reaction with just benzene. And that's because when these all have lone pair of electrons or orbitals in which they can overlap with the conjugated pi bond. And that allows them to donate electrons to the ring, which increases the electron density of the ring, which makes it a better nucleophile and therefore makes a faster reaction. For electron withdrawing groups, it's just the opposite. It's going to pull electron density out of the ring because whatever is connected to the ring is either electronegative, like the halo groups, or partially positively charged. So it's going to pull electrons away, which decreases the electron density, makes it a less good nucleophile, slows down the reaction. So these groups also have an effect on where subsequent reactions will happen. So we have ortho-pair directors, which are typically your EDDs, and then you have your meta-directors, which are typically your EWDs. The only exception to this is your halo groups. But your ortho-pair directors are going to have lone pair of electrons on them, and meta-directors are going to be partially positively charged on the atom that's connected to the ring. So, example here with an OH group connected to the ring. If I then have a nitration reaction and I want to add a nitro group to the ring, so if I attack it with this double bond here, if I add this here, attack here, add this here, I get the positive charge in this case on this carbon, and in this case I get it on this carbon. Okay, and remember these double bonds are free to move around because these electrons are delocalized. So this positive charge will move every other carbon, okay, and this one will move every other carbon. So what I want with electron donating groups is, remember I have a lone pair of electrons, I want the positive charge on this carbon. Because of these lone pair of electrons, I can neutralize this positive charge. So when I want to neutralize positive charge, this makes this more stable and therefore easier to make, okay? So for meta-directors, I have like a carbonyl group here. So because this carbon is connected to this oxygen is electronegative, it's going to pull electron density up towards itself. So this carbon will be partially positively charged. So if this atom connected to the ring here is partially positively charged, and when I add something to it, I don't want the positive charge on that carbon, right? Because then this will be positively charged, this will be positively charged. They're going to push away at each other. It's going to put a lot of bond strain here. It's going to make this unstable, which we don't want. So this is a meta director because if I add the nitro group to the meta position, I get the positive charge here, which can then go here and here, but it never ends up on this carbon where it would make that unstable bond strain. So that's why this is a meta director. So meta directors will have the partial positive charge, and then ortho pair directors will have lone pair of electrons. Make sense? Okay. So last topic that will be on your test is nucleophilic aromatic substitution. So we've been doing electrophilic aromatic substitution. So in this case, we have nucleophilic, where we want to substitute a halogen on a ring for a nucleophile. So if we have chlorobenzene mixed with sodium hydroxide, we can end up with phenol here. So hydroxide is both basic and nucleophilic. So basic is when it's donating electrons to a hydrogen, and nucleophilic is when it's donating electrons to a carbon. So in this first step, this oxygen is going to donate a pair of electrons to this hydrogen here. So in this step, this is a base, which will break this CH bond. These bonding electrons will go here to form a triple bond, which will push off this chlorine. Okay, so I made water here, and then chlorine came off here. And I end up with benzyne, which I have a triple bond here. Okay, so this is unstable. This does not want to stay like this. So now this hydroxide is going to act as a nucleophile and donate a pair of electrons to one of these triple bonded carbons, which will break that triple bond and move these bonding electrons to this carbon after that OH group adds to this carbon. Okay. So this, again, unstable, not happy, doesn't want to stay like that. So what we'll do is to neutralize that negative charge, we'll take a hydrogen from the water that we formed up here. And then we can reform OH from the water and end up with phenol. And you can do this with other nucleophiles like we talked about in class today, but they all have that benzyne intermediate. Make sense? Okay, so examples. These are some of the kind of questions you would see on a test. Is we would hypothetically give you something, a compound, and ask you how to make it. So I have a benzene ring, I have a benzoic acid group, and I have a nitro group, and they're para to each other, okay? But I know that both of these groups are meta directors, right? So I need to figure out how to put both of these groups on there, but have them be paired to each other, right? So if I start with benzene, what can I do here? What's a group that's related to this one that's a para director / ortho? So I can add an alkyl group, right? Because I can oxidize, I know I can oxidize an alkyl group to that, but I know alkyl groups are ortho pair directors. So I can have an alkylation reaction and put whatever alkyl group I want on the ring, okay? And I know this is now an ortho pair director. So now I can have nitration. Okay, so when I do nitration, I'll form both of these products. This is the only one we're concerned about, so that's what we'll continue with. But now I can oxidize that alkyl group to benzoic acid, right? And I do that with potassium permanganate. And I end up with the product that I wanted. Does that make sense? So your way to approach these problems is to figure out if they're para to each other, meta to each other, ortho to each other, and then figure out what groups you need to put on there that are related to the groups that are on there to get them to that position to each other. And then you can mess with the groups that's on there to get to your product. Does that make sense? Okay. So, same thing here. Okay, so I have a chloro group on there, and then I have NH2. I know both of these are ortho-para directors, but they're meta to each other. So, what can I do? This is the part where you answer. What was the side reaction that involved that, or the side chain reaction? Reduction of what? Yeah. So I know if I put a nitro group on the ring, I can eventually reduce a nitro group to that. And nitro groups are meta directors. So what I'll do first, have a nitration reaction. Which puts a nitro group on the ring. And then I can have halogenation. Nitro group is a meta director. So I'll end up with Cl in the meta position. And then I know I can reduce that nitro group to the group I want. So I'll reduce using tin and HCl. But remember that gets me to NH3 plus. So now I need to react with the basic salt to then get it to NH2. And that gets me to the product I want. Make sense? Yes, no? Okay. So you'll also see some of these where you have subsequent steps and you need to figure out what comes out at the end. So if I start with benzene and I react with chlorine and this catalyst, that's just a halogenation reaction. So that just puts chlorine on the ring. So now if I take this and react with CH3Cl with the same catalyst, what director is chloro group? Come on. Come on. I was on pair of electrons. You know this. Ortho para meta. What did I just say like 2 minutes ago? So it's going to be ortho para because of lone pair of electrons. Okay, so it's going to be mostly para. But you can also put the ortho. Okay, so now if I oxidize that, when I oxidize, I turn whatever alpha group I have there into benzoic acid. Okay, so after all three steps, I would end up with that. Make sense? Any questions? Okay. So, another one of these. When you do alkylation, it's much easier to just write out the mechanism than try to figure out the rearrangement just off the top of your head. So, if I have this alpha chloride react with catalyst, lone pair of electrons from chlorine will attack the aluminum. Put a negative charge on the aluminum, positive charge on the chlorine. So if I broke this bond, this carbon-chlorine bond now, that would make a primary carbocation, which can't actually be formed, but I have the option to rearrange. So this middle carbon here has a hydrogen. So I'll move this hydrogen to this carbon here, and at the same time, I break that carbon-chlorine bond. So I switch this hydrogen to this carbon here, which makes 3 methyl groups around this, and the positive charge is on this carbon here. That's a tertiary carbocation. So now I add that to the ring. Which gives me that. So I just put that in line structure, but I react this with this. I didn't write out the mechanism, but I did that a few times ago. So this is this carbon, and then these 3 are these 3. Okay, so now, after I have this product, if I have a nitration reaction, alkyl groups are again ortho-pair directors. Got a nitro group to a pair position, and then to the ortho position as well.
This one is only para directed. The TB has a styrene pigment.
My bad.
How much for?
So it's only pair director. Okay. Any questions? Okay. And I did want to show you this. I don't know if I've. Let me share my screen. I don't know if I've shown you guys this before. I don't know if I've shown you guys this before. So this is Chem2 3D. It's the website. It has a lot of cool, like, under the organic tab, it shows you a bunch of different reactions that we've done all year, and you'll continue to do. So if you go to the electrophilic aromatic substitution, you have all the options here. And this is just if, I don't know, if you're more of a visual learner, this shows you exactly how the bonds are formed, what's happening in between there. So if you find that helpful, it's ChemTube 3D, and they have a bunch of different organic reactions you can look at. If any of you have to take inorganic, I don't think you do, or any other like upper level chemistry, there's also some up there for those. So check it out if you so please. And that's it.